Yes, sir. Yes, sir.
Okay. So we have completed rectifier controlled separately excited DC motor drives. And we took single phase, full wave, fully controlled rectifier in detail. And you can have half controlled rectifier also. And you can have three phase rectifier also. The advantage of using three phase rectifiers is, first of all, that your ripple frequency increases. Okay, so that your filter size decreases. Your waveform is more closer to DC. Okay. And the third thing is chances of discontinuous conduction are decreased. Okay. Most probably you will get continuous conduction if you are using a three phase rectifier. Is that clear?
Yes, sir.
Okay. Today we start with chopper controlled DC motor drives. Okay, chopper controlled DC motor drives are utilized when you have a fixed DC supply. Okay. And you want a variable voltage DC supply, then you will use a chopper. How can you get a fixed DC supply?
So with the help of batteries.
Yes, with the help of batteries, or industrial use, you will rarely use batteries. Am I right? Right or wrong?
Yes, sir.
Industrial use, you will rarely use batteries. Batteries are used only in applications such as electric vehicles. Okay. Industrial use, if you use battery, you have to keep on changing the battery. That is a very, very difficult process. Okay. Especially if you are using for an application that is in continuous use. For intermittent use, used like once a week, once a month, for example, UPS, then okay, you can go for battery also. But for a continuous process, batteries are never going to be used in industries as of now. Okay, battery technology is not that developed. So how do you get, or do you get a
Uncontrolled
fixed?
rectifiers,
So
diode
after
rectifiers,
rectifying the
uncontrolled.
Yes, from the AC supply, you use an uncontrolled rectifier so that you get a fixed DC supply. Okay, and that fixed DC supply you can convert into a variable voltage DC by using a chopper. Okay, which switches are used in choppers? Do you use SCRs in choppers?
no, sir, transistors.
Yes.
Yeah.
Why? What is the reason?
So MOSFETs.
Why?
Because there is no commutation circuit. And
So high frequency
that's one
switching are
higher
required.
power
High
rating is
frequencies are switching
low.
switches are required. High frequency switches. Means MOSFETs,
So they
IGBT,
can
high
operate in higher
frequency.
power rating.
Okay, so the first reason is that these switches, MOSFETs, IGBTs, power transistors, they are fully controllable. You can turn on with the gate signal and you can turn off as well with the gate signal. Whereas if you use an SCR, you can only turn on. For turning off, you need a commutation circuit. So that is one reason why MOSFETs, IGBTs, and power transistors are preferred for choppers. Okay. The second reason, as Priya said, these choppers have to be operated at a very high switching frequency. If you operate the chopper at 50 hertz or 100 hertz or 200 hertz or even 500 hertz, the waveform that you will get at the output is going to be very, very poor. Okay. So we need to operate the chopper at a high switching frequency. How high? Have anyone of you simulated a chopper?
So 100 kilohertz, 50 kilohertz.
Okay. In my experience, 10 kilohertz, 20 kilohertz is sufficient. Okay, you can go higher also, but this much is sufficient. If you go higher than that, of course, your filter size decreases, your waveform further increases, but your switching losses also increase by a larger value. Okay. So 10, 20 kilohertz is sufficient for a chopper. Okay. So for these high frequencies, the most preferred device is the MOSFET. Okay. But MOSFETs have a limitation. What is the limitation?
Low power rating.
Yes, MOSFETs suffer from low power rating. So MOSFETs will be used in choppers only when you have low power applications. If you have medium power applications, then you don't use a MOSFET, you go for an IGBT. Okay. If you have a high power application, then
GTOs.
yes, GTOs and IGCT. IGCT. Okay. Search for IGCT. Okay. These IGCTs are sort of making GTOs redundant now. Okay. Instead of GTOs, people are preferring IGCTs. Search for IGCT. Okay. So Vijit, search for
High power rating, sir.
search for
IGC.
IGCT.
IGCD, okay, sir.
Very high power applications, you'll find that people are still using SCRs in choppers. Very high power applications. Okay. Chalo. So let us see some basics of chopper controlled DC drives. And once again, we are going to use the separately excited motor. Okay. So some modes we are going to see. First of all, we will see the motoring control. Okay. So this is your fixed DC supply. This is your transistor or MOSFET or IGBT, whatever you want to use here. Here you have a freewheeling diode. And after that, you have the motor armature, armature resistance, armature inductance, and the backlights, RA, LA, and E. This is your applied armature voltage VA, and this is the armature current IA. Okay. Again, in case of chopper, because you have a freewheeling option, okay, the chances of continuous conduction are highly increased. The chances of continuous conduction are highly increased, provided, of course, you have an inductance, which you will always have in case of a DC motor. If there is no inductance, then you can't get continuous conduction. But because we are studying for a DC motor, there is armature inductance, so we are not going to consider discontinuous conduction. Okay, how does this work? If you plot the waveforms of the armature voltage and the armature current, initially when the chopper is on, how will the current flow?
Exponentially
Sir,
upward.
linear increasing.
Current will flow from the supply through the transistor. This freewheeling diode will be reverse biased. It will flow through the motor and back to the supply. Correct?
Yes, sir.
Yes.
How much is the armature voltage? How much is the armature voltage?
Sir,
V.
alpha time V input.
Alpha.
Alpha time V.
No. How much is the armature voltage?
V.
Sir,
V. Correct.
Supply voltage.
When the chopper is on, the armature voltage is equal to the supply voltage.
Okay, you are asking means when a chopper is on, then how much is the voltage?
Yes.
Okay.
Okay. When you turn off the chopper, as soon as you turn off the chopper, this freewheeling diode instantly becomes forward biased because of the inductor voltage. And this armature current then freewheels through the freewheeling diode so that your armature voltage becomes zero. Once again, you turn on the chopper, again the armature voltage becomes equal to V. Okay. What will happen to the armature current? It will increase when the chopper is on, it will decrease when the chopper is off. Okay. The rate of increase and decrease will depend on the armature inductance as well as the armature resistance. Okay. So there are two intervals here. One is the duty interval. The duty interval is the one when the armature is connected across the supply or when the chopper is on. So during the duty interval, this VA, that is equal to RAIA plus LADIA by dt plus E, that will be equal to B. And the other is the freewheeling interval. Freewheeling you will get when the chopper is off. And during the freewheeling interval, this VA, that is RAIA plus LADIA by dt plus E, that will be equal to 0. Okay. So if we take this time as 0, we can call this time as the T on. And this is one cycle of the chopper operation, T. Okay. This time is T on and this time is T off. In total time, capital T is T on plus T off. The chopper frequency will be equal to 1 upon capital T, and that should be around 10 kilohertz to 20 kilohertz. Okay. Once again, as you can see, the armature voltage is not perfect DC. Okay. It has a DC component as well as harmonics. Okay. Those harmonics have to be, what do they have to be?
Shifted.
They have to be filtered.
Filter.
Shifting is done by your by the choice of your switching frequency. Okay. Now they have to be filtered. And how will you filter out these harmonics? You will simply use a capacitive filter. Okay. Capacitive filter is sufficient for chopper. Okay. So you try and simulate this. You try and simulate the chopper. Okay. First see what is the output voltage you get when the chopping frequency is low. As you increase the chopping frequency, how it improves. And then with filter and without filter, you will see that unless you connect the filter, your output waveform is very bad. Okay. But as soon as you connect a filter, even a small size, okay, you will get a perfect DC at the output. What you will get?
Perfect DC.
A perfect DC voltage at the output. Okay. How much is this perfect DC voltage? That is the average armature voltage.
Duty cycle time
Average.
Yes. So I think you have already studied. So 1 upon total time integral 0 to T on. During 0 to T on, the armature voltage is V integrated with respect to time. Okay. So this becomes T on by T multiplied by V. Or the average armature voltage is equal to, some people use alpha, some people use del. Okay. Okay. And what is del?
Duty cycles.
T on by T. T on by T.
T on by T.
T on by T. That is equal to the duty cycle of the chopper. Duty cycle or duty ratio. Okay. Define duty cycle. or duty ratio? Define. Give me a universal definition of duty cycle.
So in
The
one
time
cycle,
for which the chopper is on.
yes, sir. Yes, sir. In one cycle, means time for which chopper is on, means switch is on. Switch is on.
Okay, anyone else with a better definition?
So the percentage of time for which the chopper is on.
Different definition. Better man. I see you are going for percentage and everything. Different definition. Okay. Depends on how you want to define it. Duty cycle basically is time for which motor is connected across the supply divided by the total time. Okay. What is duty cycle? Priya, what is duty
Time.
cycle?
So means time duration means up together which our motor is DC motor is connected, armature is connected to our input supply. That
Divided
is,
by the total time. Okay, that is
yes.
the duty cycle. Okay. How much is the average armature current now? How much is it?
Del
Average
VA
armature current.
minus E divided by RA.
Correct. Del V minus E divided by RA. Why LA has not come into this?
So DC sub DC. The
Because
output
we are
is DC.
considering average values or DC values. And in steady state, inductor is like a short circuit. Okay. Then what is the equation for our speed? Omega m, that will be equal to del V upon K minus RA by K square multiplied by T. Correct? Instead of V by K, it becomes del V by K. Okay. So how are the speed torque characteristics then? If this is the natural characteristic, then these are the characteristics as you go on decreasing del. Okay? Clear?
Yes, sir.
Yes, sir.
Okay. So by concluding the value of del, which you can do by concluding the on time and the off time, you can get any desired value of armature voltage, and hence you can get any desired value of the speed of the motor. Okay? So that is how you control the speed of the motor by using a chopper. Okay. Now suppose you want braking. The advantage of using a chopper is that you can get regenerative braking down up to 0 speed. Okay. So which chopper circuit can be used?
Just step up. Step up chopper, sir.
No. Step up chopper is not for braking. Step up chopper is when you want to increase the voltage.
It's a boost converter.
What is the difference between step up chopper and boost converter? Okay, so this is one of the circuits.
Sir, LC circuit will be there, sir. LC circuit.
LC circuit.
Yes, sir. The only the filter circuit is there, and
Okay, there are a number of circuits that can be used. Okay, that is the, what do you say, fun with power electronics. A number of circuits can do the same job. Okay, so this is the circuit that you see on your screen is one of the circuits that can be used for regenerative braking. Okay. Now, how does it work? Once again, I'm going to draw the VA and IA waveforms. Let us say this is the on time, this is the off time, and so on. Okay. This is T on, and this is the total time, capital T. Okay, when the chopper is on, what will happen?
So total current will flow through the chopper.
Which current? Supply current?
No, sorry, motor current.
Motor current. Okay. The motor current is flowing because of the back EMF.
Right.
Okay. What about the armature voltage?
Say zero.
Yes, the armature voltage is zero. What will happen to the armature current? Will it increase or decrease?
Sir, increase.
Yes. Okay. Okay. So these are the waveforms when the chopper is on. What happens when the chopper is off? Does this diode become forward biased or reverse biased when the chopper is off?
Forward bias.
Sir,
Forward
reverse
bias.
bias. Reverse bias, sir. Reverse bias.
Why reverse biased?
Forward bias.
Sir, switch is off.
Hmm.
So means capacitor will make this diode reverse bias,
Why?
and input supply will come to the our motor across the our motor.
How it
We
will come across the motor if the diode is reverse biased? Will it jump like this?
the supply will not come, but it will reverse the other our diode.
So that means no current can flow.
Yes, sir.
Hmm?
Yes, sir.
Inductor current. This inductor current will instantly become zero.
So the inductor polarity will reverse, and the stored energy will supply that it will flow, make the diode forward bias.
Which components are trying to reverse bias the diode? Priya?
Yes, sir.
Which elements are trying to reverse bias the diode?
Capacitor voltage.
The supply voltage is trying to reverse bias the diode. Whereas the back EMF as well as the inductor current, when the current is flowing like this, the inductor voltage, both of them are trying to forward bias the diode. Okay? So there is a fight there. The supply voltage is saying I want the diode reverse biased, whereas the back EMF and the inductor voltage are saying that we want the diode to be forward biased. Who will win this fight? The supply voltage or inductor and back EMF?
Inductor and back.
Yes. You don't even need the back EMF there. The inductor is sufficient to forward bias the diode. Okay. How much voltage can you get across an inductor? Less than supply voltage, greater than supply voltage.
So obviously greater than supply voltage.
Yes, you can get up to infinity because it is L di by dt. And if you suddenly reduce the current to zero, inductor voltage becomes infinite. Okay. Inductor voltage is sufficient to cause current to flow through air. Inductor voltage is sufficient to cause current to flow through air. That is why you get sparking when you close the switch. Is it not?
Yes, sir. Yes, sir.
Yes. So this inductor voltage is very powerful because of which it will forward bias this diode. Okay. So now the current that was freewheeling like this, that current will now start flowing against the supply. How much is the armature voltage now? What is the value of VA?
Supply voltage.
Yes. If you look it from here, VA will be equal to RAIA plus LADIA by dt plus E, and from that side VA will be equal to the supply voltage. Okay, so VA is equal to V. What will happen to the armature current? Will it increase or decrease?
That decrease because V will E minus V by
Yes, because it is now flowing against the supply. Earlier it was freewheeling, now it has to flow against the supply. There is an opposition to the flow of this current. That is why the armature current will decrease. Once again, you turn on the chopper. Again, the current starts increasing, the voltage becomes 0. Okay? Is the working of this chopper clear?
yes sir.
Yes, sir.
Okay. Again, there are two intervals. The first one is the energy storage interval. That is from 0 to T on. When your chopper is closed, current is flowing like this, your inductor is storing energy. Okay? And the other interval is your duty interval. Okay? When your motor is connected across the supply, current is flowing like this. How much is the average armature voltage? It is equal to 1 upon T, integral from T on to T, V dt. Correct? 1 upon total time. Integral from 0 to T on is 0. So we don't consider that. Integral from T on to T. From T on to T, the armature voltage is V, integrated with respect to time. Okay. So how much does this become? It becomes T minus T on. Okay. T minus T on upon T multiplied by V. Correct?
Yes, sir.
How much is T minus T on upon T? How much is? What can I write in place of T minus T on upon T?
1 minus T
1 by 1 minus
T into V
1 minus
delta.
delta.
delta 1 minus delta into V whole.
So 1 minus delta. 1 minus delta times V.
Correct?
No, sir. No, sir. So 1
Why?
minus del. 1 minus T on upon T. T on upon T is the del. 1 minus del.
That is why I asked you for definition of duty cycle. What is duty cycle?
So V will be in the right side and VA will be in the
What is duty cycle? Time for which
Motor is operating.
motor is connected across the supply. What
Across
is
the
the time? What is the time for which motor is connected across the supply? It is T minus T on divided by the total time. Okay? So as per that definition, T minus T on upon T is the duty cycle.
Okay, sir.
Okay? It all depends on how you define it. Okay? Same circuit you can get VA is equal to V upon 1 minus del. Depends on how you define it. If you say del is T on by T, then the formula changes. But if you say del is time for which motor is connected across the supply divided by the total time, then the formula changes. Am I clear to everyone?
Yes, sir. Yes, sir.
yes sir.
It depends on how you define del. Okay? If you say that del is T on by T, you get a different formula. If you say del is time for which motor is connected across the supply divided by the total time, then you get this formula. Okay? Different books will use different formula. This big books ठीक है. Big books means reputed authors. They will always use del is time for which motor is connected across the supply divided by the total time. Okay.
Okay, sir.
P.S. Bhimra will say del is equal to T1 by T. And you must have studied from P.S. Bhimra in UG.
Yes, sir.
है ना? So you get a different formula there. ठीक है. चलो, ठीक है. So the advantage here is the formula is same both for motoring as well as regenerative braking. Correct? The armature current is now equal to del V minus E divided by RA. Okay. ठीक है. Sorry, it will not be del V minus E. It will be E minus del V upon RA. Or it is minus del V minus E upon RA. Okay. Correct. Are you with me or gone? Somewhere you have
Yes, sir.
gone.
Yes, sir.
Subhajit, Sumit and Priya, only 3 voices I hear. सुमन बोलता है कभी कभी, बाकी तो किसी की आवाज नहीं आती. Nobody. Okay. ठीक है. So we have
Yes, sir.
seen two circuits. We have seen two circuits, one for motoring and other for regenerative braking. So which class do you have after this?
Machine
What
analysis
time? What time?
3:30, sir.
अच्छा. So can I extend?
Yes, sir.
पक्का? Or do you want to study tomorrow? बोलो.
Sir, up to what time, sir?
Around 2:30. I don't want
Yeah,
to
you
hurry
can, sir.
actually.
Yes, sir. Yes.
ठीक है. So we have seen two circuits, one for motoring and one for regenerative braking. But we don't want two different circuits, है ना? You are not going to change the circuit when you suppose you want to go from motoring to regenerative braking. So instead, what we have is we have a single circuit that provides us with both motoring as well as regenerative braking. Okay. So this is your supply voltage. This is your input filter. Okay. This is your TR1, D1, TR2, D2. And this is your armature. Okay. RA, LA and E. This is your armature voltage VA, and this is your assumed positive direction of armature current IA. Okay. So now this circuit will provide us both with motoring as well as regenerative braking. When you want motoring operation, you will control TR1. You will control TR1. Okay. So when TR1 is on, current will flow from supply, TR1, armature and back to supply. Correct? And when you turn off TR1, this current will freewheel through the diode D1. Okay, is this clear?
Yes, sir.
So when you want motoring operation, you control TR1. You do not touch TR2. You only touch TR1. So if TR1 is on, current flows from supply through TR1 motor and back to supply. And when you turn off TR1, this current freewheels through diode D1. So you get the same performance that we saw in the first circuit, with the average armature voltage being equal to del V. Okay.
Yes, sir.
And when you want regenerative braking operation, then you do not touch TR1, you control TR2. Now when TR2 is on, current will flow from E TR2 and back to the motor. Okay? Current increases, your inductor stores energy. And when you turn off TR2, this same current will now flow through the diode D2 and back to the supply and back to the motor. Okay? So we are getting the same operation that we got in the other circuit for regenerative braking, with once again the average armature voltage being equal to del V. Okay, clear?
Yes, sir.
Yes, sir.
Hmm? So here we have a circuit that gives us both motoring as well as regenerative braking in the same circuit. You don't have to change the circuit. All that you have to change is which switches you are controlling. If you want motoring, you control TR1. If you want braking, you control TR2. Okay, is this clear?
Yes, sir.
Yes, sir.
ठीक है
Yes, sir.
प्रिया ठीक है
Oh, yes, sir. Yes, sir. Yes, sir.
सही बोला मैंने. Did I say the right thing? Or there was some mistake in it?
No, no, sir. No, sir.
Okay. There is still one drawback in this circuit. And the drawback is that you have to wait for some time before you go from motoring to braking. You have to wait for some time, because when you are motoring, you are controlling TR1. The armature current is flowing in one direction. And when you want braking, you are controlling TR2, so that the armature current reverses. Okay, so there is some time lag before you can go from motoring to braking. If you want fast transition from motoring to braking or braking to motoring, then you control TR1 and TR2 simultaneously. Okay, what did I say? If you want fast transition, instant transition from motoring to braking or braking to motoring, then you control TR1 and TR2 simultaneously. Okay, so how does that happen? This is the armature voltage. This is the armature current. Okay, this is the on time T on, and this is the total time capital T. Okay. Suppose initially the armature current was negative. Armature current was negative means it was flowing like this. How it was flowing? Through D2. Correct? Yes or no?
Yes, sir.
Yes, sir.
Okay. Now this is the on time. So on time you will turn on TR1. Off time you will turn on TR2. So you turn on TR1 here. Okay? During the on time you turn on TR1. Even if you turn on TR1, will it turn on? Okay? How you are turning it on? You are giving a signal in its base. Will it turn on? When the current is flowing like this, will it turn on?
Yes, sir. Yes, sir. Yes, sir.
Will the transistor turn on
Yes,
when
sir.
the
One.
current is flowing like this and you
No,
are
sir.
giving a signal in its base? The answer is no. Somebody said no. Who said no?
No, sir.
क्या नाम है जिसने अभी नो बोला पहले, सुमित के पहले?
Yes, sir. Yes.
Yes or no? Will the transistor turn on when the
No.
current is flowing like this?
Sir, negative current is flowing. How
That
it
current is
can?
flowing through the diode, not through the transistor.
So it depends upon the current, motor current.
Motor current is flowing like this through the diode. Will the transistor turn on? Very simple question. I'm surprised you are not
No,
able to answer it.
No,
Sir,
sir, no, sir.
Hmm?
Because diode is forward bias, so the transistor would be reverse
Yes,
bias.
yes. कौन था ये? नाम क्या है? Who gave this answer?
Sir, Abhishek Maji.
Hmm?
Sir, Abhishek Maji.
Abhishek Maji. Abhishek Maji has given the right answer. As long as this diode is on, your transistor is short circuited. Correct? Hmm? As long as this diode is conducting, they are connected in parallel, na? So as long as this diode is on, your transistor is short circuited. Actually, when the diode is on, the polarity across the diode is like this. This is positive, this is negative. So your transistor or your SCR or any other switch that you are using here in anti-parallel, that is reverse biased. So even if you give a gate signal, it will not turn on. Okay. So as long as this current is flowing, even if you give a signal to the transistor base, that transistor cannot turn on because it is reverse biased. Am I clear now? Yes.
Yes, sir.
Yes.
yes, sir.
What will happen to the armature current? Will it increase or decrease?
Sir, what you are saying, sir, how, sir, current will complete its path?
Through D2.
Sir, how?
D2.
Through D2 to up to?
V. Motor.
Okay, okay.
So will the current increase or decrease? Subhajit, current increase or decrease?
So decreases.
Hmm.
No
Decrease or
idea.
increase? No idea, Rikya.
Sir, actually, sir, sorry to say that, sir. I'm not able to see the cursor, sir. Sometimes.
Hmm. Now
Can
you
you
can
increase the
see.
size of
Sir, decrease, sir.
the
Will the current increase or decrease?
De-
decrease, sir?
decrease, sir.
Okay. It will decrease in this direction or it will increase in this direction. Okay. Your current is decreasing in the negative direction or increasing in the positive direction. Correct? It
Yes,
is
sir.
decreasing in the negative direction, or you can say, relatively speaking, if it is decreasing in the negative direction, so it is increasing in the positive direction. Okay. So the current will go on decreasing in the negative direction like this. What is the armature voltage? How much is the armature voltage? The armature voltage is equal to V. Correct? Even when the diode is
Supply voltage.
conducting, the armature voltage is equal to V. Correct?
Yes, sir.
है ना? This point is connected here. This point is connected here. So even when D2 is conducting, the armature voltage is equal to the supply voltage. Okay, which device is conducting here? The device conducting here is D2. So this current goes on decreasing, and after some time, this current becomes zero. As you can see here, the current becomes zero. As soon as that current becomes zero, this diode becomes reverse biased. As soon as the current becomes zero, this diode becomes reverse biased. And at that instant, if there is a signal available at the gate of this transistor will turn on. Correct? And now the current will flow from supply through transistor, motor, and back to supply. Is this clear to everyone? Kalyani, is this clear?
Yes, sir.
Yes.
Yes, sir.
Okay. So the current starts increasing and the device conducting is now TR1. The device conducting is now TR1. How much is the armature voltage when TR1 is conducting?
We,
Yes,
we, sir.
it is still V. So irrespective of whether D2 is on or whether TR1 is on. The armature voltage is equal to the supply voltage. Which device is conducting, that will depend on the current, whether it is negative or positive. Okay, here your on time is over. So you turn off TR1. And because we have decided that both TR1 and TR2 are going to be controlled simultaneously, so you turn off TR1 and you give a signal to TR2. You give a signal to TR2. You turn off TR1 and you give a signal to TR2. Now the current was flowing like this from supply to TR1 motor and back to supply. Okay. As soon as you turn off TR1, this D2 is forward biased, this D2 is reverse biased. So the current cannot flow from the supply now. Is this clear? As soon as you turn off TR1, the current cannot flow from the supply. Okay. Supply has no problem with that, but the motor has a problem because it has an inductance. The inductor current cannot become zero instantly. So the inductor current will continue to flow in the same direction. Now, what are the options it has available? It cannot go like this because this transistor is off. This
Flyback through
diode is
D1.
on. So the only option is to freewheel through D1. Freewheel through D1. Correct, everyone? What is the armature voltage when the current is flowing freewheeling through D1?
Zero.
The armature voltage is zero. Okay? Current is freewheeling through D1. Will the current increase or decrease? The current will decrease. Because there is no supply now. The current will decrease in the positive direction. Current will decrease in the positive direction or increase in the negative direction. So the current goes on decreasing, and after some time the current becomes zero. After some time the current becomes zero. At that instant, if a signal is available in the base of TR2, TR2 starts conducting and current now becomes negative and flows through TR2. Okay, your inductor starts storing energy. So your current increases in the negative direction. Your armature voltage is still zero. Whether TR2 conducts or D1 conducts, your armature is short circuited. So that armature voltage is zero. Is the working clear, everyone?
Yes, sir.
Sir, please explain the part of TR2, sir.
Okay, so when you turn off TR1, when you turn off TR1, the current was flowing in this direction. It will continue to flow in this direction and it will flow through D1. Okay? Armature voltage is zero. This current will go on decreasing and it will decrease to zero. As soon as it decreases to zero, this D1 becomes reverse biased. Now, if you turn on TR2, the current now starts flowing like this. Okay? So current starts increasing in the negative direction while your armature voltage still remains zero because the armature terminals are short circuited. Okay? Is this clear now?
Yes,
Everyone?
Yes, sir.
Okay. So because we have used the definition, what definition? The duty cycle is equal to time for which motor is connected across the supply divided by the total time. We get VA is equal to del V here. Okay? Because this is the time for which the motor is connected across the supply. TR1 or D2 are conducting. And this is the time for which motor is not connected across the supply. TR2 or D1 are conducting. Okay? So our average armature voltage becomes equal to del V. Our average armature current, that becomes equal to del V minus E divided by RA. Average armature current is del V minus E divided by RA. Okay.
Okay, sir.
Okay. So the fun is here that your armature current can be positive as well as negative. average armature current can be positive as well as negative. When will it be positive?
So
T1
during
or
motoring.
D1 on.
Hmm?
Either
क्या?
T1 or D1 on.
No, 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 no. This is average. That is what we are talking is instantaneous. This is average. It's different. Correct? What we are talking about when T1 and D1 are on, armature current is positive. When T2 or when T1 or D2 are on, when T1, D1 are on, armature current is positive. Those are instantaneous values. This is average. When will the average armature current be positive?
During motoring, it will be positive, and during
No,
regenerative
no,
braking,
no, 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 no. You have come to the conclusion that I'm trying to. ठीक है? कौन था ये? सुमन था. Suman's answer is correct, but yes, directly jump to the conclusion.
so
ठीक है?
depending on value of delta, it can be.
Yes. ये कौन था? ये भी सुमन ही था.
So when the value of delta is greater than del
Correct.
V.
When del V is greater than E, or del is greater than E upon V, then your average armature current is positive and you will get motoring operation. Okay? That is why I said Suman gave the correct answer, but he jumped to the conclusion. And when del V is less than E, or del is less than E upon V, then your average armature current is negative, so that you are getting braking operation. And when do you get the transition from motoring to braking?
When del V is equal to E.
Yes. Or del is equal to E upon V. That is the transition. Okay, so simply by controlling the value of del, you can get motoring as well as regenerative braking simultaneously from the same circuit. Okay, so it is 2:30 now. We'll stop here. Dynamic braking remains. We'll study dynamic braking tomorrow. Okay, tomorrow 3 p.m. Okay.
Okay, sir.
Any questions?